All right, let's start the second talk. It's by Chaitanya Karamchedu from the University of Maryland. So I wanted to say it's a criteria for quantum advantage, and that's very exciting, but the title changed, so that's exciting too. So please go ahead and tell us.
Okay. Thank you, everybody, for being here at the last session of the last day of the conference. I'm going to give a talk on some recent work that I've done in collaboration with Matthew Fox and Daniel Gottesman on a criterion for nominally quantum advantage, but really a criterion for post-selected universality. I'm going to justify this perhaps slightly overzealous original title as mild clickbait for getting people here on the last day. Okay, so let me go ahead and dive in. So in some sense, our entire field is predicated on this idea that there are computational tasks that you can ask a quantum computer to do that we expect that classical computers cannot do efficiently. And in complexity theoretic language, we like saying this as some sort of separation between BQP and BPP. Of course, I might not really mean decision problems. I might be asking about sampling tasks more generally. But in general, we expect there's some computational task a quantum computer can do efficiently that a classical computer cannot. But like everything in complexity theory, of course, this is hard to prove outright. And so in lieu of getting like an outright separation, what many researchers have done is taken to look very closely at this boundary that we think exists somehow between BPP and BQP. And one of the ways to do this is to build non-universal models, restricted models of quantum computation that we somehow think live on this boundary, somehow straddle it. The hope somehow being that if you can build enough of these, that somehow explore different areas on this boundary, and in fact, like get some sort of zoo over this space, you can build a very refined understanding of what the properties of this boundary might be, and get an understanding of someday in the future how to actually show some unconditional separation. Okay, so just kind of at a high level, why are these restricted computational models interesting? So for one, they kind of from a pragmatic perspective, they make showing quantum advantage, the task of showing quantum advantage, distinct from achieving universal fault-tolerant quantum computation, which we expect is hard, though, of course, as we've seen, especially over the last year, it's getting more and more tenable all the time. And from kind of a theoretical perspective, it gives you some sense, it can inform what the landscape we think between classical and quantum computation looks like. But of course, at this point, there's a very basic question that we need to answer, which is, it's very easy for me to come up with kind of stupid non-universal models that classical computers can simulate. So if I give you some non-universal quantum model, how do we know that it's likely to be classically intractable, right? And so this is the problem that we try to make some progress towards in this work, specifically by kind of studying this worst case approximation where we want to get close in multiplicative error. Okay. So our strategy for this is going to be specifically to look at non-universal quantum gate sets as a particular kind of non-universal model. So just to recap, we say that some collection of quantum gates is universal if it densely generates all possible unitaries that you can do on some number of qubits. And by Solovay-Kitaev, we know that all else being equal, universal gate sets are somehow equivalent in their computational power if we have like enough space and depth. And of course, there are many restricted models that work by playing off of restricting space and depth. But the concept here is just simply going to be to restrict some gate set to non-universality and classify its computational power. Right? And this is kind of relevant from a practical perspective for a couple of reasons. These could be easier to implement experimentally. And these could also be easier to error correct. There are all these results that show that you can't have transversal implementation of an error correcting code over universal gate sets, but you could over some of these. And it's worth just emphasizing here that this task of trying to classify even non-universal gate sets by their computational power is difficult. We don't even have like necessarily complete understanding of which gates are universal or non-universal. So just quickly going to run through some prerequisites and conventions. I imagine many of you are familiar with this. When I say BPP and BQP, what I'm really referring to are sampling tasks. This is a broader notion of computation than decision problems, but the reason why we like looking at it is because it's actually easier to show quantum advantage in this setting. And there's a lot written in our paper about this if you're interested in it. So now, actually, how do we show quantum advantage? The kind of common strategy for showing it in the multiplicative error model is to use post-selection, right? So post-selection is the ability to force the measurement outcome on a qubit given some potentially generic quantum state in kind of a single time step. And to do this in a single time step is sort of non-physical. And more generally, I should say, if you have some randomized algorithm, whether it's classical or quantum, it's the ability to somehow keep only those runs in which some particular property that you want holds. And so just to give an example of this, you can imagine having this kind of heavily weighted quantum state where you're kind of exponentially more likely to measure the state 1, 1, then 0, 0. But using post-selection, I can kind of, in a single time step, post-select on the first qubit, measuring the first qubit in the state 0, and just get the state 0, 0 out as I want. So to do this without kind of weighting is a non-physical power. But it's incredibly powerful. And so you can ask, if you were to give a computer, like a randomized classical computer or a quantum computer, the power to do post-selection, how much more powerful does it become? And the cool thing is it somehow turns out that the answer depends on whether or not you've got a classical or quantum computer. So I'm not going to go too much into the complexity theory argument here for this, but again, we go through it in our paper. But I love this analogy. It's kind of due to Adam Boland, which is, BPP is somehow like if you take your average Joe and giving him post-selection turns him into this like roided out strongman. But BQP is quite different. BQP is like starting out with your Daily Planet reporter, and then giving it post-selection is like getting Superman. And somehow, if you're claiming to me that these are equivalent, this should be something that is considered very unlikely from a complexity theory perspective. And of course, this is a very, very loose way of talking about it. But the upshot that I want to communicate here is that it turns out using post-selection as a resource actually lets you reason about the non-post-selected classes. And this turns out to be very useful for us. And the key point is that if you're given some non-universal model, but with post-selection it becomes universal for quantum computation, then there's a very standard complexity argument that shows that efficient classical computers cannot simulate this non-universal model to within small multiplicative error unless the polynomial hierarchy collapses. And the collapse of the polynomial hierarchy is considered this very unlikely complexity theoretic event. For those unfamiliar, you can think of it roughly analogous to P equals NP. If you could prove quantum advantage supposing non-collapse of the polynomial hierarchy, that would be a reason to celebrate. So let's go through a quick example of how this kind of argument might work. This is one of the kind of early ones showing this. So you can imagine this subset of set of gates that kind of defines a subset of IQP circuits. So this is just take a T gate and a control Z gate and conjugate it by Hadamard gates. There's this famous result. So first, this is an example of what your circuits over this gate set could look like. You have computational basis states, apply a layer of Hadamards, some diagonal circuit, Hadamards again, and then computational basis measurements. And there's this famous result by Bremner, Jozsa, and Shepard showing that if the polynomial hierarchy is infinite, then efficient classical computers cannot simulate circuits over this gate set to within small multiplicative error. The way this argument works is to basically use what we call post-selection gadgets to boost IQP circuits to universality. And what this looks like is you can take one of our gates, so this is the Hadamard conjugated CZ gate, and then initialize one of the qubits in the state 0 and the other qubit post-select it in the state 0. And you can kind of see you've got one free qubit where you haven't done any initializations or post-selections. And you can just do the computation of what is effectively the gate that you're applying on that circuit, on that free qubit. And it turns out if you just do the math, you're basically applying a Hadamard gate. Right? You're just applying a Hadamard gate on your qubits and then swapping them. And the key point here is that when you add in a Hadamard gate to your original gate set defining the IQP circuits that we started out with, you get a universal gate set. So in this way, you can show that IQP circuits with post-selection become universal for BQP. And this gives you the hardness result you want. A kind of more intricate example you can do quite simply using what are called conjugated Clifford circuits. So this is, you fix some single qubit unitary U and then conjugate some generating set for the Cliffords. So here we just chose Hadamard S and CZ. And now you ask the question, are there choices of your single qubit unitary U such that quantum circuits over this gate set are classically intractable? And if so, which U? So this was answered by Adam Boland and his collaborators. And the answer turns out to be yes, basically for almost all non-Clifford U. And this is kind of the formal result. I won't go into it too much, but the result is basically, if your U is basically non-Clifford, then classical computers cannot simulate this to within small multiplicative error. And again, the hardness of this kind of relies on this useful fact that Clifford plus any non-Clifford gate is universal. So now what we're going to try to do, and kind of the main work of our paper, is to generalize this result, right? This approach to showing hardness in the multiplicative error model. And the thing to note here for both this IQP and conjugated Clifford circuit example that we just went through, and in fact for most of these other known restricted models, the kind of strategy for showing multiplicative hardness is the same. You start off with some non-universal gate set S, And then you build post-selection gadgets over these, specifically unitary post-selection gadgets, which implement these gates. And now you show that when you add in these unitary gadgets into your original gate set, you get a universal gate set. This is the strategy that you go through to show hardness over this non-universal gate set S. The problem is this approach doesn't really generalize particularly well. For general non-universal gate sets, understanding what are the extra unitaries you need to add to them to lift them to universality is complicated and needs to be done more or less on a case-by-case basis. And kind of more to the point, it turns out that there are some gate sets for which it seems that unitary post-selection gadgets are actually not enough to achieve universality. Somehow you're kind of stuck doing Pauli's or Cliffords, which aren't enough to lift you. So the solution that we take in our work is quite natural. We're going to make an appeal to non-unitarity. Post-selection is a non-unitary resource. You should try to do non-unitary things. And the kind of key point we're going to take advantage of here is that if S is some non-universal gate set, we're just going to assume that your gate set S contains some entangling gate. If it didn't, then certainly there's a classical simulation of it. And now, because we assume that your gate set S contains some entangling gate, then we can basically restrict our post-selected analysis to trying to show that your gate set S with post-selection is dense in SU2. Because if it is, then you can just add in your entangling gate and then get a universal gate set for BQP. So how do we do this? We're going to basically look at a more general construction of these single-qubit post-selection gadgets, right? So what I mean by that is we're going to take that example of that circuit where, for example, we implemented a Hadamard gate, but we're going to look for a general gate set, non-universal gate set. We're going to build post-selection gadgets that look like this, where we initialize all but one wire, and then we post-select all but one wire. And this effectively implements a single-qubit gate on whatever your free wire is. Now, the useful point here is that in general, the invertible post-selection gadgets that you build, they don't need to be in SU2, but they will be in SL2C. Right? And SL2C is kind of this larger group of 2x2 single-qubit matrices, 2x2 matrices with complex entries that contains SU2 as a subgroup. So if you're able to achieve with post-selection a dense subgroup of SL2C, you're also going to densely generate SU2. Now, the lucky thing for us is that the subgroup structure of SL2C has been very deeply studied. It's very relevant in fields of algebraic geometry and Lie algebra and Lie groups. And specifically, there are these results that show the subgroup structure of SL2C is very, very highly constrained, essentially requiring that your subgroups are either going to be discrete or dense in SL2C. And there are these results, like this one due to Sullivan, that shows that if you've got any finitely generated subgroup of SL2C, then if it satisfies these three mathematical properties called non-elementarity, non-discreteness, and strict loxodromy, then that subgroup that it generates must necessarily be dense in SL2C. Now, I haven't actually explained what non-elementary, non-discrete, and strictly loxodromic mean. I'll give some intuition for that in a moment. But the thing I kind of want to emphasize at the moment is that these properties are quite easy to test. Specifically for us, it's going to boil down that testing these properties just reduces to computing traces of elements of your gates. And again, your gates are going to be 2x2 matrices. So computing the traces is just adding two numbers. Just as an example, if you want to compute test for non-elementarity of some 2-generated subgroup of SL2C, you only need to compute these two functions that are just two functions of the traces of your generators. So putting together the theory of the subgroup structure of SL2C, along with some complexity theory arguments that we work out, you can put this all together to get a criterion for realizing post-selected universality with a non-universal gate set. This is kind of our main result. So altogether, what it comes out to say is that if you've got some non-universal gate set and you suppose that the polynomial hierarchy is infinite, then if you have some finite collection of these single qubit post-selection gadgets, that's what we denote by this GAD1 of S, such that you can show that it's non-elementary, non-discrete, and strictly loxodromic, then you can immediately conclude, as soon as you've met those three things, that no classical computer could efficiently simulate circuits of your non-universal gate set to within small multiplicative error. And just to kind of open up the conversation a little bit and give some intuition for these three mathematical properties, very roughly what non-elementary means is that when you're given post-selection, your gate set should be able to do more than just unitary things. Right? Because post-selection is a non-unitary resource, your gate set should somehow be able to leverage access to that non-unitarity. Non-discreteness means the kind of standard topological thing, meaning that your gate set needs to have limit points. You need to be able to approximate things. And strict loxodromy is this interesting one where basically you require that your gate set should have fundamentally complex elements. You need to have some generator that has complex trace. And I just want to point out here, we actually expect that the strict loxodromy condition is unnecessary, and it's an open problem to try to extricate this from our criterion. And I'll talk a little bit more about that at the end. So, with this criterion, we want to be able to prove some things with it. It wouldn't be particularly useful if you couldn't do anything with it. So that's kind of what we're going to go into next. So some applications. So one of the first things you can do with this is you can reproduce in basically 2 steps. You can derive extremely simple proofs for the hardness of IQP circuits and conjugated Clifford circuits. Basically, it boils down to the identification of 2 or 3 gadgets and then just computing some traces and showing that they meet the criterion that you want. But more interestingly, we want to prove new things. So what we kind of do is we look back at these conjugated Clifford circuits, right? So this is the generating set that we have for the conjugated Clifford circuits for some fixed U. And what you can ask is, what if I just remove one of these gates, right? So let's just say I remove the Hadamard gate, the conjugated Hadamard gate, and I just look at this gate set. This gate set is somehow characterizing commuting conjugated Clifford circuits. These 2 gates commute with each other. You can ask, do these retain the classical intractability that you want? And it turns out yes. But it turns out kind of even more remarkably, I can just do away with the S gate too. And I can just look at a conjugated CZ gate. So this is an incredibly weak gate set. It's a single gate. It commutes with itself, of course. But it turns out that if the polynomial hierarchy is infinite, then efficient classical computers cannot simulate even circuits over this gate to within small multiplicative error. And we, by the way, fully classify the choices of U for which you actually achieve this hardness result. And it basically is almost all non-Clifford choices of U. So this result actually closes an open question that Bolin raised in his work on conjugated Clifford circuits. Now, of course, once you've kind of played that game, there's a more general family of questions you can ask, which is what about when you just take these conjugated Clifford circuits and restrict them to particular subgroups of the Clifford group? There's, for example, a classification of the subgroups of the Clifford group done by Luke Schaefer and Daniel Greer, where you get this kind of subgroup lattice. And in our work, we're actually able to show that if you basically take any of these subgroups, so long as they contain an entangling gate, any of these subgroups conjugated by almost any single qubit unitary retains the classical hardness result, which is quite remarkable given that some of these are very, very weak. And so we actually hope to put out some forthcoming work fully exploring this lattice. OK, so with that, I'm just going to go on to some open questions that I want to raise. So there are a couple ways we actually expect that our criterion for this multiplicative hardness result can be improved. One of them is to understand the structure of post-selection gadgets under inverses. So one of the requirements that we have in our criterion is that you need to be able to show that any SL2C operation that you can perform with post-selection can also be realized, its inverse can also be realized over your non-universal gate set. Now, it turns out that in practice, this is almost always true. But this is difficult to mathematically prove. So one major step forward would be to be able to show that you could realize inverses exactly with post-selection. As I mentioned earlier, we actually expect that the strict loxodromy condition is unnecessary, this requirement that you're able to realize fundamentally complex elements. The kind of intuitive reason for this is that real quantum computation is also classically intractable. It's universal for quantum computation. So somehow the requirement that you have complex elements seems superfluous. So extricating this requirement would also be very, very nice, and you could just reduce it to those 2 constraints that you want your gate set to meet. And then lastly, I kind of want to go into the discussion that kind of started this talk, which is using this criterion, you're able to reason about some very, very weak and simplified restricted models, like these conjugated CZ circuits. And one of the things we would hope is that this criterion will basically ease the identification of these candidates for non-universal models realizing classical intractability. So one thing we would hope, for example, is that using this kind of criterion, you can refine the understanding of this BPP-BQP boundary by understanding how these non-universal models might relate to each other. So a very simple question you could ask, for example, is if you take these conjugated CZ circuits, and then given 2 different single qubit unitaries, U and U prime, I could ask, what are the sampling tasks that over conjugated CZ circuits with your unitary U, which of those can be simulated by conjugated CZ circuits conjugated by a U prime? And how do these different single QP unitaries relate to each other? And then finally, of course, this is all with respect to multiplicative hardness, right? And as many of us know, this isn't really the most physically appropriate model of error that we would like to show hardness for. We would really like to show hardness in the average case, right? So this is kind of additive error. Now, there are kind of a couple ingredients that you need to take a worst case multiplicative hardness result into an additive case hardness result. Of course, there's a tremendous amount of research going into that right now. But one thing you can ask is, are there other generalized criterion that you can formulate in order to show that non-universal gate sets realize some of these other criterion? For example, could you develop a criterion for non-universal gate sets to realize anti-concentration in addition to this worst case hardness? This would be like a very interesting thing if you were able to show it, of course. And of course, the kind of worst to average case reduction is one of the hardest steps of this, but nonetheless, we leave this as an open question as well. So with that, I think I'll just say thank you and open the floor up for questions.
Thank you very much for a very enlightening talk. I'm sure there are a lot of questions. So.
Thanks for the talk. Maybe it's a naive question, but so I would be curious to know the characterization of the unitary, the conjugated CZ. I mean, they also include diagonal gates, which are non-Clifford, or?
Sorry, so for these conjugated CZ circuits, yeah? Sorry, what was the question?
I mean, what about their characterization? I mean, you told that you characterize them, and,
yes.
And they can also be diagonal non-Clifford gates, or?
No, so if they're diagonal, then of course it'll be classically simulable just because you're never leaving the computational basis states. But so essentially what you can do, for example, is you can take your single qubit unitary and parameterize it by Euler angles. And what really boils down to is you can reduce this U to be an Rx theta gate. And so long as your Rx theta gate is not theta is equal to pi by 2, so as long as it's not Clifford, then these realize the multiplicative hardness result.
Okay, makes sense. Thank you.
Thanks for the talk. I was just wondering, I think maybe I missed something when you were talking about the deconstruction of the Clifford gates. You were saying for most of them it's still hard. What does it mean that for like some of them it's not hard?
So for, was this when we were talking about the conjugated Clifford circuits as a whole, like the Boland result, or towards the end of the talk?
Towards the end of the talk, you were saying like, oh, some of these are not hard, but you're adding this to the CZ gates, right? Like no matter what gate you add to your gate set, if you already have the CZ gate, then by your result, it would still be hard.
Well, so not all subgroups of the Clifford group, even if they're contained entangling gates, contain a CC gate. So for example, you can look at one of these fragments contains this gate called a T4 gate. So this is kind of non-trivially different from a control Z gate, for instance. So you can have higher order entangling gates that somehow could be even weaker than CC gates in principle.
Okay, thanks. Yeah. So you're not adding to the CZ gate. It's
no,
separate, totally separate gate sets.
Yep, exactly.
Thank you.
So you had a condition about the gate set being like a bit complex, right? It should have like a properly complex element, something about the traces there.
Yes. So the complex element means like literally it should have a real part and an imaginary part.
Yeah.
So yeah.
Can you just not enforce that by just adding like a gate that just adds a global phase?
No, I don't think that works. There are like some technical reasons why just trying to impose a global phase doesn't actually get you enough to beat the strict loxodromia requirement. Yeah.
More questions? Okay, I have a question.
Yeah.
So I have a question about IQP circuits in general. So there are some results and experiments that people try to run IQP circuits on fault-tolerant platforms, also at the University of Maryland, yes. I believe, yes. And so would your results or have any implication, or do you have intuition? Like they claim that it's hard to simulate. They choose the error-correcting code, then run the IQP circuit on it. So do you think it's going to have for practicality for a given circuit to claim the hardness of the simulation, such consequences?
I don't know, because one of the hard things with, again, we're all just reasoning in the multiplicative error model, and the problem is the threshold theorem for fault tolerance only guarantees the robustness of quantum computation up to additive error. Now, with IQP circuits, there's been a lot showing that you can do this anti-concentration arguments and then get this, at least conjectures for worst average case reduction. And all that we don't consider at all. So what we hope is that this kind of criterion gives you a very easy prescription for identifying these with this worst case hardness. And then there's a lot more infrastructure that needs to be built around showing these criterion for anti-concentration and worst average case hardness reductions. But I think it's very hard to make the leap directly to the practical side, yeah.
Okay. Well, still. Thank you very much.